To add these polynomials, we're going to combine like terms. So let's see, we have a 4x to the fifth and a 10x to the fifth, so that is 14x to the fifth. Okay, now I'm going to drop down to x to the fourths. There aren't any here, but there is one over here, meaning it doesn't combine with anything. So then I'll put, let's see, a 5x to the fourth. If I go now to the x cubes, again, there's only one, so we have plus 2x cubed. All right, for x squareds, we have a 5x squared and a negative 3x squared, which adds to 2x squared. There are no x's, and now if I just combine the numbers, here I have 1 and 9 being added together, so we get 10. Adding these two polynomials, let's see what we have. The highest exponent is an x to the seventh, so here I have a negative 1 and a positive 21. So it leaves us with 20x to the seventh. X to the sixth would be the next one down, so I have a positive 95, but a negative 4 here. So that is a positive 91x to the sixth. There are no x to the fifths all the way down to x squared, so there are none of those, but we do have a 3x and a 2x, which adds to a 5x. There's only a number remaining, and that is negative 1 at the very end, and this is the final answer. All right, so adding these two polynomials, an x to the 42nd power is here and here. All right, so we have 11.5 plus 1.5, that's 12.5, so up to 13. 13x to the power 42. Dropping all the way down to the next closest power is going to be an x to the fifth, but there's only one of those, so I get plus 3.5x to the fifth. Okay, now, again, we don't have anything until we get to an x to the first power, which is a 7.5, and we are subtracting 10.5, which would give us a total of negative 3x, and then there are no numbers. We've combined all like terms. To subtract two polynomials, essentially what we do is just distribute this negative to every term in this set of parentheses. And in fact, we don't even need to write the parentheses over here since there's just a 1 in front of it. So I'm going to rewrite the problem. The problem would be, okay, we have 1/2 x cubed plus 1/3 x squared minus x minus 6. And by distributing the negative in the next set of parentheses, meaning it just gets multiplied to these four terms, we have negative 1/3 x cubed plus 1/2 x squared plus x minus 2. The sign changes on all of them. Okay, now we can start looking at the x cubes, and that is a 1/2 minus 1/3. So, I'm really just looking at this number and this number. If I get a common denominator of 6, that leaves me with a positive 1/6 x cubed. Now we move on to the x squareds. So this one is going to be 1/3 plus 1/2. Again, a common denominator of 6 would give us a fraction of 5/6 x squared. Okay, we now have x's. There's a negative x and a positive x. Those just completely cancel. You could put 0x, but I'm not actually going to write that. And then lastly, we have this negative 6 and negative 2, which combines to a negative 8, and that's the answer. Again, distributing this negative to, again, 4 terms in the parentheses is just going to change the sign, so let's rewrite the problem. That problem would be, okay, we got 15x to the 10th plus x to the 8th plus x to the 6th plus x, but then we get a negative 10x to the 15th minus x to the 8th plus x to the 4th plus 1. And for like terms, I'm looking for the largest exponent, which is a 15. This means my first term will be negative 10x to the 15th, because that does not combine with anything. The next closest one, if we drop down, is going to be an x to the 10th. There's only one of those, and that's a positive 15x to the 10th. We next have x to the power of 8, All right, here we have some like terms. There's a positive and negative x to the 8th, meaning they just completely cancel. I won't write it. Going down to the next exponent would be an x to the 6th. There's only one of those. Then we have an x to the 4th. Again, there's only one of those. There's an x to the 1st power, and yet again, one of them. And then a plus 1 at the very end. And this is the difference of these two polynomials. For question 6, here we have several things that we're doing. We're both adding and subtracting, but the idea is the same. I think one example will get this point across, where what I'm going to do is distribute the negative to all of the terms in this polynomial, and then at the very end I'll just add this on. So it's like just throwing in another couple of terms. So let's rewrite the problem. That is, you have 90x to the 7th plus 5x cubed plus 8x squared plus 10. Nothing really happened there. But when I distribute the negative, I get negative 50 x to the 7th plus x cubed plus x squared minus 9x, and then plus 4x to the 7th minus, it should be a minus x cubed. And let's see, so if I start looking for like terms, the largest exponent is the x to the 7th. We have 90 here, negative 50 here, but then a positive 4 here. So I'll do this as 90 minus 50, which is 40, and I'll add 4 to give me 44x to the 7th. There are no x to the 6th or 5th or 4th, but there are x cubes. There's 5 here, there's 1 here, and there's a negative 1 here, which leaves us with 5 minus 1, well, sorry, 5 plus 1 minus 1, which is just 5. So we get 5x cubed. Okay, now looking for x squareds. Okay, here we do have a couple of those, right? Here we have an 8x squared, and then one more, so that's a total of 9x squared. Now if I look for an x to the 1st power, there's only one of those. It's minus 9x, so I'll just copy that down. And then there's only one number, which is 10. And so this is my final answer. Okay, I'm going to use the distributive property to multiply these two polynomials together. 2x gets multiplied to both terms, and then this 1 gets multiplied to both terms as well. When we do that, we get 6x squared plus 10x plus 3x plus 5. The last thing to do is combine any like terms, and there are 2 in the middle. That's a total of 13 x's with a 5 at the end. All right, again, multiplying in both x squared and 1. Starting with x squared, we get 2x to the 5th minus x to the 4th plus 2x squared. And when we multiply in the 1, I'm going to do that trick again where I'm going to write stuff below. So if I multiply in the 1, I get a 2x cubed, but there are no 2x cubed, so I'll write that off to the side. I get a negative x squared, which I'll put below the x squareds. And then I also get a plus 2. And lining all of those up and adding them, I get a 2x to the 5th, a minus x to the 4th. I see there's that 2x cubed there. I'm just going to go ahead and write that next. And then I'll subtract the x squareds to leave me with a positive 1x squared and a positive 2 at the end, and that's the final answer. So multiplying these two, okay, starting with the 3x, that gives us 18x to the power of 6. Then I get a negative 3x to the 4th. I'm going to leave some space in case an x to the 5th shows up this time. All right, if I multiply a 3x to an x, I get negative x squared. Again, maybe I'll leave some space for an x cubed if that shows up. Multiplying the 3x to a 1 gives me 3x. Now multiplying in the negative 2, we get negative 12x to the 5th. So now I actually left myself some space to line things up just a little bit more carefully. If I multiply the negative 2 to the negative x squared, that's a positive 2x squared. Then a negative 2 to a negative x is a positive 2x, and a negative 2 at the very end. And we're adding all of this stuff up. Maybe put that here. So we get 18x to the 6th minus 12x to the 5th minus 3x to the 4th. There were no x cubes. We now have a negative 1x squared and a positive 2x squared, so that's just a positive x squared plus 5x minus 2, the final answer. So for this one, in the last question where I tried lining things up, I'll try to do that as best I can here, but sometimes it really isn't possible. Let's see what we get. Multiplying in the x to the 5th gives us an x to the 15th. The fact that we have such a large exponent makes me think there might be like a lot of gaps. So if I multiply x to the 5th to an x to the 8th, that gives me an x to the 13th. And then I would have an x to the 8th. So maybe I'll just put that like way over here. I'm going to try to do this as best I can. Multiplying in negative x cubed, I get negative x to the 13th. Okay, so that lines up there. I get a negative x to the 11th. And then a negative x to the 4th. Okay, so I was able to do this pretty well here. Where when I add these together, our final answer is x to the 15th. There are no x to the 13ths. There's a minus x to the 11th, a plus x to the 8th, and then a minus x to the 4th. For this question, I'm distributing in 3 separate terms, meaning I'll have 3 lines this time instead of 2. But for this, multiplying in x squared, we get 2x cubed, and then plus x squared. Multiplying in a negative x gives us a negative 2x squared minus x, and multiplying in 1 gives us 2x plus 1. 3 lines because we multiplied in 3 terms. Adding all of this stuff up gives us 2x cubed minus x squared plus x plus 1. Just a thought with this process. Multiplication is commutative. You could rewrite this over here, or simply just distribute in the x squared and the 4 if you want simply 2 lines to write, but just keeping it consistent to what I've done, I'm going to multiply in each of those 4 terms, giving me 4 lines. This is a completely appropriate way to do it. We get, by multiplying in the x cubes, we get an x to the 5th plus a 4x cubed. And I'll leave some space for possibly an x to the 4th, which I get. If I multiply in the negative x squared, I get negative x to the 4th minus 4x squared. Multiplying in the x gives me an x cubed and a 4x. Multiplying in a negative 1 gives me negative x squared minus 4. So these are the 4 lines that I'm adding up. And what I get is x to the 5th minus x to the 4th. Okay, now I have a couple of x cubes. In fact, I have a total of 5. Then a negative 5x squared plus 4x minus 4. All right, multiplying this in, starting with the x to the 4th, would give us a 5x to the 7th minus an x to the 6th plus an x to the 5th plus 2x to the 4th, multiplying in the negative 2. Wow, we jump like way down the line, so that gives us, hopefully if I left enough room, we get negative 10x cubed plus 2x squared minus 2x minus 4. So this one was spaced apart so much that, kind of like in retrospect, I see there is nothing that can be combined as a like term. We get 5x to the 7th minus x to the 6th plus x to the 5th plus 2x to the 4th. Why am I even writing this line down? You could have just left the above line, but I guess just keeping it consistent, we end up with this minus 4 at the end, and there is our answer. Okay, so multiplying these two together would give us 16x to the 4th minus 8x cubed minus 4x squared. Multiplying in the 2x gives me 8x cubed, then a minus 4x squared, and then minus 2x. Multiplying in 1 gives me 4x squared minus 2x minus 1. Adding these up, we have 16x to the 4th. The x cubes cancel. We have a negative 4x squared, a minus 4x, and a minus 1. For the polynomial division, I'm just going to set up the problem where it's x plus 1 divided into 2x squared plus 7x plus 5 instead of just rewriting it as in the homework, so starting here. The goal is to cancel a 2x squared, so I would have to multiply by a 2x, because 2x times x is 2x squared, but also 2x times 1 is plus 2x. I am taking the difference of this, I'm subtracting it away. The 2x's cancel, and then 7x minus 2x is 5x. Bring down the next term and proceed. Okay, I want to cancel 5x, so okay, clearly I'm going to multiply by plus 5. This is going to work out perfectly. We get 5x plus 5, and by taking the difference of these two things gives me a remainder of 0. So what this means is, I'll write out for maybe a couple of these questions. The answer is 2x plus 5 with a remainder of 0. But we are essentially saying that if you were to take x plus 1 and multiply it to 2x plus 5, it is equal to 2x squared plus 7x plus 5. Multiplication would take you to this, and the process of division divides things apart. There's a remainder of 0, which technically gets added here, but no point in really writing plus 0. That's the answer. If you understand how division works, there's not going to be too much of a surprise to the answer here. But anyway, 2x plus 5 divided into 2x squared plus 7x plus 5, I would want to first multiply by x. That gives me a 2x squared, but also a plus 5x. And if I take the difference, I get 2x plus 5. So clearly the only last thing to do is multiply by 1. These two things match up perfectly, and I have a remainder of 0. Not a big surprise here, because x plus 1 times 2x plus 5, as we already know, is equal to 2x squared plus 7x plus 5. So 15 and 16 are closely related. If you divide by this factor, you get 2x plus 5. If you divide by 2x plus 5, the answer would be x plus 1. All right, so for this one, I want to cancel 6x cubed. I'm going to multiply by a 3x squared. That lines up the 6x cubed perfectly, but you also get negative 3x squared. And when you take the difference, okay, here you're subtracting a negative. Negative x squared plus 3x squared is really a 2x squared. So what we're doing there is, I'll draw it in here, but this is really minus a minus becomes addition. You don't have to write that every time, but that is what happens. It's really a positive 3 and a negative 1. So keeping that in mind, I'll bring down the positive 7x. Canceling a 2x squared means I have to multiply by x. I get 2x squared minus x. And okay, again, here I have a minus, so 7 really plus x is 8x, and I'll bring down the minus 4. Okay, I would have to multiply by positive 4. if I want to match up this 8x minus 4, hey, this one works out perfectly where you have a remainder of 0. I won't write it out, but what this tells me is if I multiply this and this together, the answer would be 6x cubed minus x squared plus 7x minus 4. All right, so here I want to divide by 5x plus 3. Notice that all the powers from 4 down to 1 and then a number at the end appears. So if 1 was missing, we would have to still place that in here with like a 0x cubed or something like that. It didn't happen. This is going to work out nicely. I want to cancel 5x to the 4th, so I'm going to multiply by x cubed. Because I get 5x to the 4th, but also a positive 3x cubed. And when I take the difference, that's a negative 2 minus 3 is a negative 5x cubed, bringing down the negative 3x squared. So now I want to multiply by negative x squared. Okay, I get negative 5x cubed minus 3x squared. When I take the difference, something odd happens here. The x squareds cancel, and so do the 5x cubes. So I have 0x squared. I'm just going to bring down the 10x. Yeah, you could write 0 here if you'd like, but you don't have to. You can simply bring down this term. So this is interesting. What would I multiply 5x by to cancel a 10x? And I know the answer is 2. All this means for us is we're going to skip over the x's. The x's do not play a role in here. If you multiply by an x, it's going to give you an x squared, which we eliminated from the problem. What I'm going to do, just for reference, is say we don't have to use the x's. All I'm going to do is skip over and bring down that positive 6. And so I'm now going to cancel a 10x by multiplying by 2. That does give me 10x plus 6. Those two things are exactly the same, giving me a remainder of 0. So in your answer, you really don't need to write these x's. You can place it there just to maybe avoid some confusion. But since the x squareds cancel to give me 0, that means I did not need to use any x's. All right, so for this one, I placed in a 0x cubed, 0x squared, and 0x. And this was because I want to use those places as a reference. So to cancel an x to the 4th, I'd multiply by an x cubed. So I just wanted to make sure that I had a spot for my x cubes. You do get x to the 4th, but also minus x cubed. And when you take the difference of these two things, you're left with a positive x cubed. And then you can bring down the 0x squared. I need to multiply by an x squared because it gives me x cubed minus x squared. And again, when we take the difference, that's going to be a positive x squared, and I'll bring down the 0x. I'm now multiplying by x, which gives me x squared minus x. And when I take the difference, yet again, we have an x minus 1, and positive 1 will line these things up perfectly so that when I take the difference, I have a remainder of 0. For this problem, I put in a 0x to the 5th because 1 did not appear within the polynomial. Let's see if we even need that. To get an x to the 6th, I'm going to multiply by x to the 4th. So this one's different too because I have an x squared here, and all the previous questions just had an x to the 1st power. So now I just have to be a little bit careful. I have to put a 4 next to this to take it up to the 6th, so I'm really just skipping over the x to the 5th and dropping down to this spot here. When the exponent was 1, we just kind of moved 1 back. When the exponent is 2, it looks like we're moving 2 places back. Well, anyway, with that in mind, I'm going to multiply by a 1x to the 4th because we get x to the 6th and also x to the 4th. And when we take the difference of these two things, they cancel, meaning I'll just bring down this negative x cubed. Okay, so now I'll multiply by negative x. So it gives me negative x cubed minus x And so that means I'm actually going to bring down that negative x. And when I take the difference here, those are the same, so I get 0. And what I haven't dealt with is that 3x squared and the 3, so I'm going to bring those down too. So we get 3x squared plus 3. Oh, all right, so now I just multiply by 3. So we get 3x squared plus 3, and when I take the difference here, I get 0. So my answer, you could place, that's it. I mean, we've definitely canceled everything, just going through it. Got rid of the x to the 6th, there are no x to the 5ths to consider. Canceled all of those. Yeah, so here it is up here. It's just x to the 4th minus x plus 3. All right, so dividing these, I'm going to multiply first by x squared. Gives me x cubed plus 2x squared. Taking the difference, we get 5x squared. Bring down the 12x. I'll now multiply by 5x. So I get 5x squared plus 10x. Taking the difference gives me 2x plus 10. This one isn't going to work out where I have a remainder of 0. There's going to be some stuff left over. But I have to cancel the x's, so I'm going to multiply by 2. I get 2x plus 4, and when I take the difference, I get 6. So I do have a non-zero remainder in this case. I'm going to write out what this means. What this means is, if we multiply by the x plus 2 times this here, it takes us to this, but we need to go 6 further to make them equal. So as a statement, that is, if we take x plus 2 and we multiply it to x squared plus 5x plus 2, the result is almost x cubed plus 7x squared plus 12x plus 10. But I have to add in this remainder to make it work out perfectly. So said another way, these things are not factors of this expression because we have a non-zero remainder. And the last division problem here in question 22, 3x plus 7 divided into this polynomial. I'm seeing some larger numbers, so I just got my calculator out just to make sure, hopefully I don't make an arithmetic error. Let's see, I want to cancel 9x to the 4th, so I'm going to multiply by 3x cubed. That gives me 9x to the 4th and also negative 21x cubed. Okay, so I take the difference. That's really going to be negative 12 plus 21, which is a positive 9x cubed minus 45x squared. So now I want to multiply by 3x squared, because that gives me 9x cubed minus 21x squared. And here, taking the difference, that's really negative 45 plus 21, which is a negative 24. That makes sense. I'll bring down the positive 98 and, 98x, and we'll continue. So I'm going to multiply by negative 8x because that matches up the negative 24x squared. But then we get a positive 56x. And when I subtract these things, that's 98 minus 56, which is 42, minus 106, which, okay, 3 goes into that 14 times? Yeah. Okay, so next I need to cancel 42x, so I'm going to multiply by positive 14, and I get, let's see, we have 42x. 14 times 7 is a negative 98. And when I take the difference, that's really negative 106 plus 98, which is negative 8. Okay. What all of this work tells me is that 3x plus 7 did not divide evenly into this polynomial. This is what came out, but you then have to subtract 8 to balance this type of equation. To determine the greatest common factor between these two terms, so let's see, I want the greatest common factor. I'll look at the numbers first and the variable second. The most I can take out of both in terms of the numbers is 7, since it divides both 7 and 21, and it's the smaller of the two. I can take out an x to the first power, again, because I have 2 here, I have 1 here. The most that you could take out of both is just x to the first. I'm going to use this to now factor this expression. I'll write the greatest common factor, and then in parentheses write what is left over if I take it out. It would have to be x plus 3. The way I check to see that this is correct is simply by distributing back to see if it takes me to my previous step. 7x times x definitely gives me 7x squared, and then 7x times 3 is a 21 and an x. Here the greatest common factor is going to be, I can take 10 out of both as well as an x squared. That's the most that can be removed. And this gives me 10x squared times 2x minus 1. All right, the greatest common factor here is 2 and x. When I factor that out, I'm left with 3x to the 4th minus 4. And it might be worthwhile, like if you're not confident about your greatest common factor, you can look at the remaining terms and say, well, is there more stuff that can come out? You can't take out an x to the 4th because there are no x's here. 3 and 4 share no other factors than 1, so this is the final answer. All right, here the greatest common factor is going to be 3 and x to the 6th. And if I remove that, I'm left with 5x to the 4th minus 7, and that is it. Here I think the greatest common factor would have to be 25 and x cubed. So my expression, if I factor that out, there's 4x and a 3. In this problem, we now have 3 terms, but the idea is the same. To find the greatest common factor, we just have to scan all 3 terms. So focusing on the numbers, we have 21, 24, and 18. Well, 3 definitely goes into all of them, so I'm going to start with that. I believe that would be the most I can take out in terms of just the numbers. And I have an x cubed squared and an x to the first, so 3x is the most that I can take out of all of those. If this is true, what remains would have to be 7x squared plus 8x minus 6. And 7x squared, 8x, and minus 6 share no common factors. So here the greatest common factor among these 3 terms looks like 7 can go into all 3 of those numbers, and an x to the first power, which means if I take out 7x, I'm left with 2x to the 4th plus x squared minus 7. So here the greatest common factor is a little bit different, but the idea is the same, where this and this, even though they're in parentheses and have multiple terms themselves, I'm going to consider that as one object. So for this problem, my greatest common factor is going to be x plus 1. 2x and the 3, they have nothing in common, so if I do factor this out, if I take out that x plus 1, all that would remain would be the 2x and the 3. So that is, this and this remain. All right, so my greatest common factor here, now this time I definitely, like in the last problem, have that x minus 7 common to both, but there's also a 4 common to both the 4 and the 8. That can be removed too. So really, 4 times x minus 7 is what can be removed, and what is left over is going to be x minus 2. All right, so here the greatest common factor, again, we get that 2x plus 1 can be removed, but now there's an x that still is common to both x cubed and x. Removing those, that is factoring out x times 2x plus 1, would leave me with x squared minus 4. For the remaining problems in the homework, the goal is to factor the trinomial or the polynomial, whatever it happens to be, And if you can use a guess and check approach, I would definitely try that first. But if it's too hard, we're going to use a different method. I think this one is simple enough to factor where I'm going to set up two parentheses and just reason my way through what the factors have to be. An x and an x and a positive would be the only options for this process to work. I need two numbers that multiply to 15 and add to 8, and those to me would be a 3 and a 5. Again, what I'm saying here is that the 3 times 5 multiplies to the 15, yet 3 plus 5 gives me 8. If this happens, that's the factorization. All right, same idea here. I'm going to try to guess what the factors are. Two numbers that multiply to 14 yet add to 9 would have to be 2 and 7. For this problem, again trying to guess, I have an x and an x. The middle term is negative and the last term is positive. That means that both factors have to have a negative in it. The product of two negative numbers is positive, yet it would sum to a negative value. So let's see, focusing on a 32, 8 and 4 multiply to 32, yet if they're negative, would add to negative 12. All right, x squared minus x minus 42. I need a positive and a negative this time. That's the only possibility since the last number is negative. So 6 and 7 multiply to 42. And if I make the 6 positive and the 7 negative, that would add to a negative 1. This is the answer. All right, let's see. Again, would have to be a positive times a negative. So I'm multiplying to 27. All right, so I'm thinking 9 and 3. If it's a positive 3 and a negative 9, that multiplies to negative 27, yet adds to a negative 6. For this one, let's see. Again, we have to have a positive and a negative if this is going to work out nicely. So it's got to be a positive 10 and a negative 5. The product would be negative 50, yet the sum of those two numbers is positive 5. All right, for this, let's see. This situation would be an x minus and an x minus. And 7 times 7 is 49, and the sum of that is negative 14, so 7 and 7 will be the answer. Here, the factors are actually the same. This falls into a special case where you could write this as x minus 7 squared, since both factors are equal. So here, maybe guessing won't be as obvious. I think I might be able to guess the answer to this one. I'm going to take that approach first. Let's see. It's definitely not as obvious, though. For this to work, we can't have just x and x. It would either have to be like 1 and 4 or 2 and 2. I'm just going to guess 2 and 2. If I want a 1 at the end, the only choice would be a plus 1 and a plus 1. But here, I want to be a little bit more careful when I verify my work. I'm going to check my answer since I'm guessing. 2x and 2x is definitely 4x squared. 1 and 1 is definitely this plus 1. What about that 4x? Where is that coming from? That's your outer terms, which is 2x times 1, and your inner terms, which is 1 times 2x. And this actually did happen to work. We get 4x squared, 2x and 2x is 4x, and plus 1. So if the guess and check method, if you factor this by guessing, and you have a number here and you're just not confident about the middle term, it might be a good idea to check your work. I multiplied it out, it matches up. Therefore, my guess is correct. Questions 41 and 42 have kind of like a similar idea behind them, where I don't have an x squared, but I have an x to the 4th, and the middle term is x squared. If I want to take a guess and check approach of factoring this, the idea is going to be very similar to what we've already done. The only difference is it's not going to just be x and x. Instead, it'll be x squared and x squared, because that is the only way you're going to multiply nicely to an x to the 4th. and I know everything has to be positive, and since I chose an x squared and an x squared, it means my middle terms will also be x squared. So I just have to come now with two numbers that multiply to a 7 yet add to a positive 8. And so those numbers would obviously be 1 and 7. So the only real difference here, like looking back at this, instead of just having x and x, I switched it to x squared and used the exact same logic up to this point, noting that x squared times x squared is x to the fourth, and your middle terms are going to be x squareds instead of x's. If we try this in 42, since they're similar, 42 is x to the fourth plus 7x squared plus 10. So again, I mean, this should work the same way, where the middle term is x squared, the first term is an x to the fourth. I'm going to try x squared and x squared for both. I'll have to put a plus sign on both of them. I need two numbers that multiply to 10 yet add to 7. That would have to be 2 and 5. For this question, I'm going to employ a trick. I don't really want to guess and check on this one. Feel free to, you might be able to get the answer, but I want to use this other strategy that appeared in the lessons in Moodle. The trick is, I'm going to take the first and last term and I'm going to multiply them together. So I'm going to look at 2 times 24. And when I do that, I get 48. The second step is to somehow take factors of 48 that combine to give me a negative 19. So those would have to be, all right, it took a little bit of guesswork here, but it's going to be negative 3 and negative 16. Those multiply to a positive 48, yet add to a negative 19. So the only difference here is because this first number, since it was not a 1, I had to now multiply these two numbers and focus on finding numbers that multiply to 48, yet add to negative 19. Continuing with this trick, what we're going to do is take the original equation, which was 2x squared, but when I get to the middle term, I'm going to split it up using the two numbers that we have over here. I'm going to write this as minus 3x minus 16x, and I'll put the positive 24 at the end. The first equation and the second one, these are identical. If I combine those, it would take me back to negative 19. What I'm going to do now is take out the greatest common factor from the first two terms and the last two terms. For the first two terms, that greatest common factor is simply x. It leaves me with x squared, 2x minus 3. And in the next two, I'm going to take out negative, I think 8 can come out of both of those. And when I do, I get 2x minus 3. So what this trick does is when you factor in this way, it should make this set of parentheses equal to this one. You can now remove this from both terms. So that is, I factor out 2x minus 3 and copy down what's left over, and that is x minus 8, and this is my final answer. All right, again, I'm going back to this trick of, I'm going to multiply 3 and 8, and this gives me 24. And now I want to find two factors of 24 that add to a positive 10, and those are going to be 4 and 6. Product is 24, the sum is 10. I go to my equation, the original one, and instead of writing 10x, I'm going to write 4x and 6x. By the way, you could have put 6x and 4x, and this process will still work. There's nothing wrong with that. I chose to do it this way. I now take out the greatest common factor from the first and last two terms separately. For the first two terms, it's just x, leaving me with 3x plus 4. And the last two terms, the most I can take out is 2. And the good news is that also leaves me with 3x plus 4. I now factor out that 3x plus 4. And what is left over is x plus 2, and that's the final answer. Taking the 5 and the 6 and multiplying those together gives me 30. I want factors of 30 that multiply to 30, obviously, but add to a negative 31. It's actually pretty easy for this one. It's got to be negative 1 and negative 30. The sum of those is negative 31. My equation is 5x. I'm going to try flipping these around this time just to show you it should still work no matter what order you put them in. I'm going to put that negative 30x first and then negative 1x second. From the first and last two terms, I will go ahead and remove the greatest common factor. In the first two terms, it's 5x. I'm left with x minus 6. For the last two terms, if I take out a negative 1, I'm left with x minus 6 as well. And if I remove that x minus 6 from both terms, I'm left with 5x minus, and really there's a 1 there, so minus 1. All right, so for this one here, same idea. I'm going to use 3 and negative 10. The product of those two things is negative 30. And I want two factors of negative 30 that add to a negative 1. That's got to be negative 6 and positive 5. So I'll write this as 3x squared minus 6x plus 5x minus 10. From, again, the first and last two terms, I'll remove the greatest common factor. I get 3x for the first one. That leaves me with x minus 2. And from the last two, I take out 5, and I'm also left with x minus 2. That's a good thing because I can now take x minus 2 out from both terms, and I'm left with 3x plus 5. All right, so now I'm doing the same thing for 10 and 2, looking at that product, which is going to be 20. And now I want two factors of 20 that add to a positive 9. Okay, after a little bit of thought there, that was 4 and 5. Let's see if this works out. We have 10x squared. It does not matter if I put the 4 or the 5 first, so I'll go plus 4x, then plus 5x, plus 2. Removing my greatest common factor from the first and last two terms. Okay, we get 2x, and I'm left with 5x plus 2. The greatest common factor between the last two terms is a 1. I'm actually going to write that in ahead of time this time, but we get 5x plus 2 is left over. And if I remove that 5x plus 2, I am left with 2x plus 1. Okay, for 6 and 14, okay, values are getting larger, but the product of those two numbers is 84. And I want factors of 84 that add to 25. Okay, let's see, 84, just like guessing a few things here. Okay, I took 84 and I divided it by 4. And when I did that, I got 21 left over, and that adds to 25. All right, great. That means we have 6x squared plus 4x plus 21x plus 14. Looking at the greatest common factor between the first and last two terms, I can take out 2x, leaving 3x plus 2 left over. I can take out 7, and again I get 3x plus 2 left over. Factoring out the 3x plus 2 gives me 2x plus 7. So this problem, I still have to try to guess the factors or use this factor by grouping approach, but I'm noticing there is a greatest common factor between the three terms. If I first remove that, it's going to make solving this a little bit easier. I can take 2x out from everything. And if I do that, I'm left with x squared plus 6x plus 5. I don't think I need to use this factor by grouping method because 2x is done, and I believe we could guess the factors of x squared plus 6x plus 5. It's got to be x and x, it's got to be positive and positive, and 1 and 5 multiplied to 5, yet add to positive 6. This is the answer. If you can remove a greatest common factor, I would say do that first. Starting with a greatest common factor, I can take an x cubed out from every term, as well as 3. So if I do 3x cubed, what remains is 3x squared minus 2x minus 5. So here, again, you could try to guess the factors, but why not just take those two numbers, 3 and negative 5, write it as negative 15, and then think about what are two factors of negative 15 that would add to a negative 2. Okay, actually that's going to be a -5 and a +3. So what I'm going to do is within the set of parentheses, I'm going to add those two terms in there. So I'm going to copy this down with the 3x cubed, but inside the parentheses, I'm going to write minus 5x plus 3x and then minus 5. So I'm doing the same idea, but I'm ignoring that 3x cubed out front. So I'm looking at the first and last two terms of this expression and removing the greatest common factor between them. For the first one, it's just x, and we're left over with 3x minus 5. For the last two, it's just 1, and I'm left with a 3x minus 5. So I have 3x cubed. I'm going to get like an extra set of parentheses, but I can just get rid of it at the very end. I'm removing 3x minus 5 from both terms, and I'm left with x plus 1. And if you see this ahead of time, you can just like erase the parentheses and express your answer as 3x cubed times 3x minus 5 times x plus 1, and that is it. All right, again, we have this greatest common factor of, it's just going to be x's since the very first term has a 1 in front of it, so I can remove an x to the 5th. This is x to the 5th times x squared minus 3x plus 42. Can I just simply guess the factors here? If I can, it's got to be x minus and x minus, two numbers that multiply to 42 yet add to a -3. All right, so I really just went through every possibility and I couldn't find anything that worked. So what this means is I can't actually do this. And this is my final answer. It is a possibility that you could end up with an equation that can't be broken apart. So that happened here, and I'll leave it as this. All right, so for this one, the greatest common factor, we could take out an x to the 6th. I'm hoping 12 divides into all three of these numbers. I'm just going to check that. 12 went evenly into both 216 and 972. That means you can actually remove 12 from every single term. That is, I can take out 12 as well as x to the 6th, and what is left over is x squared plus 18. That's what I got when I divided 216 by 12. So it's really 18x. And then plus 81. That's what I got when I divided 972 by 12. Are we going to have a situation again where like we can't actually factor this apart? I don't know. Let's see. X plus and x plus, we're really just doing this by guessing. So two numbers that multiply to 81, you gotta add to 18 would be 9 and 9. You can leave your answer like this, or if you'd like, you can write 12x to the 6th, and then you can say x plus 9 squared. So both of these are acceptable. Okay, we can definitely remove a greatest common factor here. Can definitely take out x to the 8th, but you can remove 4 from every single one of those terms. So that is 4x to the 8th. And what remains is going to be 2x to the 4th minus 3x squared and then minus 5. So here, I don't have an x squared and x, I have an x to the 4th and an x squared, but that's okay. When we factor this apart, we're just going to try to remove now an x squared. So we'll have like two pieces with x squareds instead of just x's. So this means we can still use that factor by grouping approach where I'm going to take this 2 and this -5, look at their product, which that's -10, and I want two numbers that will add to -3, which is going to be -5 yet +2. So this will be very similar to all the work we've done. I'll have 4 times x to the 8th. I'm going to rewrite this expression as 2x to the 4th. I'll go minus 5x squared. So it's an x squared instead of an x this time, but it'll still all work out. Then I'll put plus 2x squared and minus 5. All right, let's see if this worked. Again, using this idea of taking out the greatest common factor from the first and last two terms. We have 4x to the 8th. I can take out x squared from both, leaving me with 2x squared minus 5. And I can only take a 1 out from the last two terms, but that's okay. Because now I have 4x to the 8th. Inside the parentheses, I'll factor out the 2x squared minus 5, and I'm left with x squared plus 1. And I don't need to write down those parentheses, the extra set of parentheses, so I'll write it as this. Now, technically, we're going to end this process here. You might be able to factor this apart, but the second you can't guess, we're going to need some more sophisticated methods that we just don't have at this point. So I'm going to call this the final answer. With what we know in this class, this is as far as we could take it. For the last problem, this is technically not a trinomial, it's the only one that doesn't have 3 terms, but I still want to try to factor this thing. And I'm going to remove the greatest common factor. So between the x to the 6th and the x squared, you can only take out an x squared. And then between 135 and 60, okay, it took a little bit of work, but 15 is the most that you can take out of both of those. Just try dividing some numbers into both 135 and 60. You can take out 15x squared, and what remains, so right, 135, when I divided it by 15, I got 9, so you get 9x to the 4th. And when you take 15, obviously out of 60, that's going to leave you with 4, so you get minus 4. And so we have this thing. We have 15x squared. And like at this point, it doesn't really look like we have a good procedure for breaking this apart, but I'm actually going to introduce this as a trinomial. By that I mean, I'm going to leave the 15x squared alone, but inside the parentheses, I'm going to put plus 0x squared to see if that helps me with this process. I'm going to take the 9 and the negative 4, multiply to give me negative 36. So I need two factors that multiply to negative 36, add to 0. Okay, that's going to be negative 6 and positive 6. What we have is 15x squared. Inside I'll write 9x to the 4th. I'll put negative 6x squared plus 6x squared minus 4. From the first and last two terms, I'll remove my greatest common factor, see what we end up with. That's 15x squared. Okay, I can take out a 3x squared. That leaves me with 3x squared minus 2. And if I take out 2, I'm left with 3x squared minus 2, meaning I can now remove the 3x squared minus 2 with a 3x squared plus 2 left over, or just simply 15x squared, and I only need one set of parentheses. Again, there's something more going on here. We just don't know enough up to this point. I think we've factored this as far as we can go.